Hello everyone and welcome back to my channel. We have been discussing the methods to estimate heritability and this is the fifth video on this topic. In my first video on this topic, I talked about the methods to estimate broad sense and narrow sense heritability. In that video, I also discussed the estimation of broad sense heritability using twins data. In part 2, I talked about the estimation of narrow sense heritability using regression of offspring on one parent. In part 3, I talked about the estimation of narrow sense heritability using regression of offspring on mid-parent. In part 4, I talked about the estimation of narrow sense heritability using correlation between relatives. So if you didn't watch all of these videos, I would recommend you to watch them before watching this one to better understand these concepts. So in this video, I will talk about the estimation of narrow sense heritability using analysis of variance, which is also known as ANOVA or intraclass correlation method. So let's start our today's topic on estimation of narrow sense heritability using intraclass correlation between half Sibs. But before actually estimating heritability using this method, I would like to give you an overview about this method. First we will see what are the half Sibs. Half Sibs are the animals who have one parent in common. So these animals only have one parent in common and that parent might be the male parent or female parent. Contrary to half Sibs, we have full Sibs, which are the animals with both parents in common. So now we will look on the assumptions for this method. This method can only be used if you have equal number of progeny per sire group, and this method can be useful for the animals with long generation interval like buffalo, cattle or camel, etc. And in this method each sire is mated to several dams and each dam produces one offspring. So now we will calculate narrow sense heritability using intraclass correlation between half Sibs. So here is the data set. In this data set there are four sires each mated to four dams. So we have four sires and each of the sire is mated to four dams and each dam produced four offspring. The average daily milk yield has been recorded on the offspring. So this first column shows sire 1's offspring, this second column shows sire 2's offspring, this third column shows sire 3's offspring, and sire 4's offspring are present in this fourth column. This first offspring is actually the offspring of sire 1 and dam 1. This second one is the offspring of sire 1 dam 2 and so on. Similarly here in this second column, this first phenotypic information is on the offspring of sire 2 dam 1 and sire, this second one is sire 2 dam 2 and so on. I hope now you have understood this data set. Okay, so this is the data set and I also calculated some extra information which will be used to actually estimate heritability. So I have calculated sum of x1, which this sum of x2 is actually the average milk production of the offspring of sire 2 and so on. So in each group we have four individuals. So this n1 is 4, n2 is 4, n3 is 4, and n4. So now we will calculate heritability using this data. First you have to make a table which is also known as ANOVA table. So this is the ANOVA table. The first column is for the source of variation, the second column is degree of freedom, the third column is sum of squares, fourth column is mean sum of squares, and this fifth extra column is expected mean squares. First we will see what are the source of variations. So in this data set we have two sources of variation. One is between sires and the other one is within sire. Within sire source of variation is also sometimes called as residual or error. So we have two source of variation. One is between sires source of variation, and the second one is the within sires source of variation, which is also known as residual or error. To calculate the degrees of freedom for between sires, the formula is s minus 1. Okay, here s is for total number of sires. So total number of sires minus 1 is at the degree of freedom for between sires. And to calculate the degrees of freedom within sires, the formula is n minus s. So this n is total number of observations. So n is the total number of observation minus the total number of sires. To calculate sum of squares, we have this formula on which I will talk later on. And to calculate sum of squares within side, the formula is in this fourth column we have to calculate mean sum of squares. The formula to calculate mean sum of squares between sides is equal to sum of square between sides divided by degrees of freedom between sides. And to calculate mean sum of squares within sides, the formula is sum of squares within side divided by degrees of freedom within side. Okay, and this last column is the expected mean squares. This formula will be used to calculate the heritability in this method. So now we will actually calculate heritability using analysis of variance. So firstly you have to calculate correction factor, which is denoted as CF. The formula for correction factor is sum of x square. So you have to sum up all of the observations and then square up and divide it by the total number of observations, which are 16. So the sum of average daily milk yield for all of the individuals is 114. So you have to square up 114 and divide it by the total number of observations, which are 16. So it would become like 12,996 divided by 16, which is actually the 812.25. Okay, so our correction factor is 812.25. The second step is the calculation of crude total sum of squares. Okay, so how will you calculate crude total sum of squares? You have to square up each value within your data set. So you will start from the first value, that was 5. So square up 5, then square up the second value, and then square up the third value, and at the end you have to sum up all of the squares. So this would be the crude total sum of squares. Okay, you have to square each of the value and then you have to sum up all of the squares. That would become the crude total sum of square, which is equal to 910. Okay, so now we have calculated crude correction factor, we have calculated crude total sum of squares. The next step is the calculation of corrected total sum of square, which I denoted with core total sum of squares, which you can also call as corrected total sum of square. The formula to calculate corrected total sum of squares is equal to crude total sum of squares minus correction factor. So we have crude total sum of square is equal to 910. So 910 minus correction factor, that is 812.25. So 910 minus 812.25 is equal to 97.75. Okay, so now we have correction factor, we have crude total sum of square, and we also calculated corrected total sum of square. So next step is the calculation of between side sum of square. So how you will calculate between side sum of square? The formula is summation xi square divided by ni. This I stands for the columns or groups. So the sum of observations for sire 1 is equal to 37. The sum of observation for sire 2 is 24. For sire 3 it is also 24. For sire 4 it is 29. Okay, and within each group we have 4 numbers. Okay, we will put all of these information in the formula. So first we will write 37, that is the sum of x1, then square up and divide it by the 4, plus sum of x2, which is 24 square, plus sum of x3, that is also 24, and at the end the sum of x4, that is 29. So after calculation you will get 28.25, that is sum of square between sides, or between side sum of squares. The fifth step is the calculation of within side sum of square. Within side sum of square can be calculated by subtracting sum of square between side from the corrected total sum of square. So the formula to calculate within side sum of square is equal to corrected total sum of square minus sum of squares between sides, that is equal to 97.75. We have corrected total sum of square 97.75. So and sum of square between side is 28.25. So after subtraction, the within side sum of square is 969.5. Okay, and now we will put all of these things in the table and calculate the mean sum of squares. Okay, so this is again the analysis of variance table. Degree of freedom was calculated by s minus 1, that is number of sides minus 1. So we have 4 number of sides, 4 minus 1, that is equal to 3. N minus, to calculate within sides degrees of freedom, the formula is n minus s. N is the total number of observations minus the number of sides. So we have 16 number of observations and 4 number of sides. So 16 minus 4, that is equal to 12. The sum of squares, which I have already calculated in the previous slide, and you have seen how we calculated the sum of squares between sides, that was 28.25. Sum of squares within side is also calculated in previous slide, so it was 69.5. Okay, so now we will calculate the mean sum of squares. To calculate the mean sum of squares for between sires, the formula is sum of squares between sires divided by degrees of freedom between sires. So sum of squares between sires was 28.25 and degrees of freedom for between sires is 3. So 28.25 divided by 3, that is 9.42. We also have to calculate mean sum of squares within sire, that and the formula is sum of squares within sire divided by degrees of freedom within sire. So sum of square within sire was 69.50 divided by 12, that is the degrees of freedom, and mean sum of squares for within sire is equal to 5.79. Okay, so now we will calculate the components of phenotypic variance and corresponding heritability using this data. So first we will estimate the variance components. The first variance components is sigma square s, which is the sire variance. So sigma square s is sire variance. The formula is to calculate sire variance is mean sum of square between sires minus mean sum of square within sire divided by k. This k is the number of observation in a group. So mean sum of square between sire is 9.42 and mean sum of square within sire is 5.79 divided by k is equal to 4. So after calculation, the sire variance is 0.91. So this is the sire variance. So and the uh, error variance are within sire variance. uh, so we also have to calculate error variance or within sire variance. So this sigma square w is for error variance equal to mean sum of square within sire, that was 5.79. Okay, so now we will calculate the phenotypic variance. Sigma square p denotes for phenotypic variance. So phenotypic variance is equal to sire variance plus error variance. This sigma square s is for sire variance, this sigma square w is for error variance. So sigma square p is equal to 0.91 plus 5.79, that is equal to 6.70. Okay, so this is phenotypic variance, and as we are using intra-class correlation method, so intra-class correlation is denoted by T. The formula for intra-class correlation is sigma sire variance divided by sire variance plus error variance. And as we are using data on half sibs, so the heritability would be 4 times to intra-class correlation. If we were using the full sibs, then the heritability would be twice to intra-class correlation. But as we are using data on half sib, so heritability is 4 times to intra-class correlation RT. So we will multiply 4 with this formula. Okay, this formula is now here. So I only added 4 to this formula. So to calculate heritability using intra-class correlation between half sibs, the formula is h square is equal to 4 sire variance divided by sire variance plus error variance. And after solution you will get this, and at the end, after solving this equation, the estimate of heritability is equal to 0.54. I hope now you can calculate this heritability using different methods which I have talked in my previous videos and in this video.